Our world stands at a critical situation where the increasing demand for energy, driven by industrial growth and modern lifestyles, has led to significant carbon emissions, climate change, and resource depletion. There is an urgent need for energy-intensive industries to radically transform their production processes in order to reach the carbon neutrality challenges by 2050. Initiatives such as the SEMWAVE project are supporting Europe's energy transition.
The SEMWAVE project is addressing these challenges by focusing on one of the highest energy demanding sectors, as steelmaking. In particular, he will propose the application of ceramic matrix composites materials in radiant tube furnaces, thus leading to an energy efficiency improvement of about 30% of their processes, by then reducing also the carbon dioxide emissions of about 20%, and also increasing the lifetime of such equipment of 20% in view of the transition to renewable energy sources.
Ceramic matrix composites are not entirely new materials. They've been around for about 30 years now, but they are really developing fast these days, and there's a tremendous interest globally in using them. And the question is why? They are materials which are very high temperature capabilities, in general higher temperature than most metals. They offer very good toughnesses compared to the straightforward uncomposite, the advanced ceramic material. So these are being looked at by a very wide range of industry, from the military right the way through aerospace and into manufacturing industry. And this is a global phenomenon.
These materials can be distinguished in oxide and non-oxide based materials, where the main composite components, namely the reinforcement and the matrix, are both based respectively on oxide materials like alumina or non-oxide materials as carbon and silicon carbide.
Due to the high raw materials and processing costs, CMCs are currently employed only in niche areas.
In the framework of the SEMWAVE project, we would like to propose the application of an innovative microwave-assisted chemical vapor infiltration technology to manufacture economic ceramic matrix composites, reducing strongly the processing time involved to manufacture them, while at the same time making their usage more sustainable.
The final goal will be a test of a CMC tubular-shaped prototype to be applied in future relevant environments characterized by fuel mixture with increasing hydrogen contents for the application in radiant tube furnaces in steelmaking application.
Several challenges have been successfully tackled along the project, which first step dealt with the development of CMC's preforms, reinforced with coated fibers.
Handling of ceramic fibers is quite challenging due to the fact that ceramic fibers are very stiff, and they become even stiffer once the interface coating is deposited on them. So we need specific routes to be able to achieve stable ceramic composites preforms.
The preform architecture depends on the winding angle using the winding machine for both for the oxide and non-oxide preforms. And we have here in the same way two aspects which we have to care about. The first aspect is that we get enough open porosity in non-oxide and oxide preforms for the later microwave-assisted CDI densifications of the matrix. And on the other hand, we also have to look on the mechanics of the system. When we only focus on the porosity, then may the tube have no mechanical strength in the later high temperature application.
To achieve weak interface composites, all the ceramic fibers were previously coated.
Normally, the coating is necessary to protect the fiber against corrosive attack. during the later application at high temperature or during the process of manufacturing. And the other thing is that the coating is necessary to weaken the bonding to the matrix, so that you really have a weakened interface between the fiber and the matrix. We use a multi-layer system, which we apply by using wet chemical infiltration technique from a roll-to-roll point of view. So there we can coat the fibers in a continuous way. So this is very important for the low-cost aspect in this project. This would be the first time in the world that we have an aluminum oxide, fiber-reinforced aluminum oxide, where the matrix is absolutely dense and not very porous.
We have gone down a different route with braiding of silicon carbide fiber to produce solid preforms that we can then infiltrate and densify with isothermal CVI to produce silicon carbide CMC tubes and elbows. We have then taken these structures and joined them with further isothermal CVI processing, and these are going to be tested at the university, at the Politecnico di Torino, for their joint strength.
Then, the CMC tubes were delivered to the University of Pisa and the University of Birmingham for further densification through subsequent matrix infiltration.
ATL have been working with the University of Birmingham to develop processes and equipment for the production of oxide CMCs by microwave CVI, which is completely novel and has not been done before. With the University of Pisa and CNRS, we have been developing upgrades for their system to allow them to deposit carbon interface coatings on preform material, and also to improve their microwave CVI silicon carbide process.
The manufacturing of oxide-based CMCs required a microwave-absorbing coating to heat the fiber-reinforced preforms up to 600 degrees Celsius.
We are trying to take materials which don't absorb microwave energy and therefore don't get hot, and heat them with microwaves, and heat them inside out with microwaves. So our goal here is to try and develop materials which operate on a different mechanism, known as weak interface, where the interface between the fibers and the matrix is, as its name implies, weak. This gives you a high toughness, but also much greater strength.
One of the major challenges has always been the control and tailoring of a well-defined heating pattern on preforms. The replacement of magnetrons with the latest solid-state sources that, thanks to the fast and precise control of the frequency, will allow a finer tuning of the operating parameters to achieve a higher quality product.
The University of Pisa defined the best operating conditions for the silicon carbide matrix densification process of the preforms using the frequency tunability of the microwave solid-state sources system. This process was guided by the National Research Council of Italy, developing electromagnetic thermal models, thus maximizing both the energy and the chemical process efficiency.
We make the real-life filtration test by using the reactors owned by University of Pisa and the University of Birmingham. And then we have also a good and strong relationship with a partner providing the electromagnetic sources, which is Frick-Muller, and also with a partner, IRIS, that is helping us to build automatic procedure of the control of the reactor. The approach we followed to obtain this monitoring of the dielectric properties during the filtration process was based on the design of the reactor as a multi-frequency system. We basically determine the way in which the samples of interest interact with the electromagnetic fields. This information is crucial because it gives the possibility to compare the efficiency of the microwave-assisted chemical processing with other more standard techniques. The optimization of the microwave heating process from the electromagnetic thermal point of view is based on the numerical modeling, of the mathematical modeling of the reactor loaded by the sample.
This modeling is multi-physics modeling in the fact that we have to combine many physical and chemical phenomena together. The center of the process is heat transfer. So we absolutely need to have a good idea of what are the thermal gradients in the material, what are the temperatures everywhere.
What we do is to calculate in the system the electromagnetic field distribution inside the reactor and inside the sample, and also the temperature distribution inside the sample for different microwave frequencies and power. Then we take a look to the results with the idea of finding what we call the optimal working conditions in order to have the best possible temperature uniformity inside the sample.
To produce a radiant tube, you need high thermomechanical properties and very specific thermophysical properties. In particular, because these tubes became hot and have to transfer heat.
We can characterize CMC samples with different densification levels. In particular, what we are going to do with this apparatus is to determine the thermal diffusivity of the sample. That is a fundamental parameter that explains how fast the heat diffuses through the sample. Thanks to these results, we can provide reliable input to the modeling activities. The modeling activities will be aimed at describing the behavior of the radiant tube in real working environment.
Advanced modeling was also applied for designing specific ceramic inlays to be inserted inside of the heater's tubes.
These ceramic inlays are designed to maximize heat transfer from the burnt gases to the walls of the tube so that the walls of the tube may radiate more efficiently on steel. And the design was based on computation, first on CAD, computer-aided design, properly designing the structure. And the second part was to achieve thermal computation, thermal transfer computation in order to assess what would be the heat transfer exactly using those structures inside the tube and try to quantify the amount of efficiency that these inlays would bring to the whole radiant tube.
Different tests were performed to measure the emissivity of the materials to deduce heat exchanged by radiation, and the performance of the materials was assessed after aging in representative atmospheres containing carbon dioxide, water vapor, and nitrogen.
And we could check that the combination of them would give something understandable. This is already one point, and the other point is that we checked too that we could understand exactly the rate of material transformation at its surface and internal surface area by the effect of oxidation or corrosion. And out of that, we could also see the impact on the mechanical properties of the material and could check that the evolution of mechanical properties and of structural transformation was slow enough to guarantee the possibility of using this material in the required ambiences.
Multidisciplinary research activities are crucial to abate both the production and the material cost as the market will grow, fostering innovation and enabling the development of new material processes in order to bring these materials to the market. In this framework, the SEMWAY project worked not only to CMC's manufacturing technologies, but also to a series of more enabling technologies as joining and coating.
In particular, we are able to find the most suitable materials that can join these both oxide and non-oxide composites that are produced in this project, and also their characterization after obtaining a successful joint. This part, it's actually a tube that it's divided in 3 sections. The one that will operate at higher temperature, for example, up to 1,300 degrees, will be used with non-oxide CMC, so silicon carbide composites, while for the lower part of the tubes that will operate at lower temperature, it will be manufactured by means of oxide-based CMC. In this case, alumina-based or alumina-zirconia-based CMC. Many materials have been tested for the joining in the SEMWAVE project. In the joining of oxide-based CMC, we managed to obtain 2 successful glass ceramic for the joining of this composite, and we also managed to publish a scientific paper in this regard. We are also using another material, for example, brazing alloys, for the joining of both oxide and non-oxide CMC. In this case, we need to have different brazing alloys for the 2 different properties of the composites.
At the same time, environmental barrier coatings were applied to act as a barrier to protect the CMC material.
EBC coatings are extremely important to CMCs. Without them, the CMC material would be exposed to extreme steam oxidation environments that would cause severe degradation to the mechanical properties of the CMC. So for the EBC coatings, we apply a novel aerosol-assisted CVD process, wherein we take precursor compounds. As far as we can tell, this hasn't actually been done for EBC coatings in the past and is completely novel to the SEMWAVE project.
Finally, the CMC tubes have been tested at industrial operating conditions in a steel-making plant using a specialized pilot-scale furnace developed by ArcelorMittal in Spain and employing fuel mixtures and hydrogen.
En un tubo real hemos quitado una parte de ese tubo y hemos diseñado un portamuestras para poder meter la muestra de este material, que es más pequeño. No era posible construir un tubo completamente con este nuevo material. Lo vamos a poner dentro de la cámara de combustión y vamos a añadir un quemador que va a quemar el gas, en este caso hidrógeno, para que el tubo caliente hasta una temperatura de trabajo, que podría ser unos 900 grados o 1000, dependiendo de las condiciones, y vamos a hacer un seguimiento del comportamiento de este material por medio de una sensórica que se ha definido para este proyecto.
IRIS developed a system on a 360 degrees view of high-resolution thermal cameras to monitor the thermal efficiency of the CMC tube inserted in the furnace. But the scale adaptation was one of the major hurdles to overcome.
Estás pasando al final prácticamente de lo que es un laboratorio, una escala de laboratorio, te estás saltando la planta piloto y estás intentando hacerlo sobre un demostrador de una planta industrial con las condiciones industriales. Entonces, al final son prácticamente 2 cambios de escala. Entonces, lo que haces en cada uno de los cambios de escala es modificar mucho los parámetros de control. Entonces, al final, tanto para nosotros como para el resto de partners, esa confluencia entre lo pequeño y lo industrial, yo creo que ha sido el mayor reto para todos.
Lo que vamos a lograr de este proyecto es todo el conocimiento necesario para poder plantearnos una segunda etapa de ya industrialización del material en sí.
Funding such as the Horizon 2020 program is extremely important for R&D activities and for industry, wider industry, because you need to be innovating to move forward with technology and science and research so that you can make contributions to energy security or health, or there are so many applications for these technologies that have quite a low TRL level, but have the potential to really change the world.
This is the time to make our energy system more resilient, secure, and affordable for industrial applications. Research on materials that can survive extreme environments and fluctuating conditions is key to transitioning to renewable energy sources. Addressing the energy crisis will open new opportunities for the industry, driving innovation and growth.